today. But postdoc at UC Irvine, working on climate regimes across habitable zones of dim stars. So Anna, I'll turn it over to you. Thank you so much.
Thank you. Okay, so yeah, today we're going to be talking about the teeny tiny Earth-sized planets that we hope to find around M and K dwarf stars. I use dim stars because I give this talk to both Earth science and astronomy, and so you'll see a hint of that dual nature throughout this talk. So some things, the background will be a little bit jumbled there. With that in mind, I actually thought I'd do a little bit of background about where I'm coming from. I consider myself sort of more a climate scientist and who's becoming an astronomer, but juggling in between these two worlds. When I was working on my PhD and trying to sum it all together, the unifying factor was to say that I work on water worlds and care about planets that may or may have water, and whether that's in the solar system or beyond it. That was my overarching thesis category. I spent a while thinking about Enceladus and its ocean, trying to use some of the techniques we use to study the Southern Ocean around Antarctica to say something about the ocean circulation on Enceladus. When I wasn't doing that, I was thinking about Earth as an exoplanet and seeing what we can leverage from Earth, and trying to sort of just slowly turn every Earth science professor at Caltech into a planetary scientist. And there's a lot of reasons for us to really want to keep coming back to Earth, even as astronomers. It's of course our best studied water world, and I don't think I need to tell this audience, but we care about water because it's the ingredient for life, so of course we want to find water. We will never understand an exoplanet as well as we understand Earth. Earth has a lot of really cool data sources that allow us to peer into its past and its present. We can see it from space. We can dive into the ocean. We track the ocean temperature, the atmosphere, the land, everything. And yet we still don't understand it very well. As an astronomer, it's easy to take for granted our understanding of climate sciences, but just ask a climate scientist what will Earth look like in 500 years. And that should give you a sense of, some of the problems we still have. And so I'd like to start with this just to, one, remind us that we're still, working on the climate side of things. We barely understand our own planet. But two, you guys have JWST and HWO, which are really cool. They're not as cute as an instrumented seal. So I like to keep this slide. Anyhow, so during my PhD, I wanted to just spend a couple of minutes talking about one result. It'll be really quick, and then I'll get to exoplanets properly. But we're working with Earth as an exoplanet and trying to go back to the fundamentals of understanding of the energy budget and the water budget of an Earth-like planet as we start edging our way into more extreme scenarios. So really naive question, what happens to Earth if we just knock it over? A little bit further. How does that energy budget respond, right? On Earth, your strongest circulation is in the low latitudes due to your Hadley cell. What happens when you start dumping that energy into the high latitudes instead? And so one kind of fun result from this was looking at what happened to the water vapor in the atmosphere, and I want to just show you the little animation. I promise I won't dive too deep into the dynamics here, but we're just looking at the seasonal cycle here. Insolation's going from northern hemisphere summer right now, and we slowly make our way to southern hemisphere summer. Let's take a look at the water vapor response. You're looking at the vertical profile of water vapor, southern hemisphere, northern hemisphere summer. Water vapor is following the insolation pattern, kind of as you might expect. In the Earth-like case for low obliquity, you're getting most of your water vapor in the low latitudes, and it's just being advected around with a season. For high latitudes, you notice, of course, it's maximizing at the poles where your insolation maximizes. You get higher values. And advection plays a smaller role because advection's mostly able to move it in the low latitudes. Instead, you're just evaporating and condensing locally a lot of that water vapor, which naively seems fine enough. But if you watch this really closely, you'll notice that the water vapor lags behind the insolation. And it's a little subtle here. Hopefully you can tell in the animation. But in reality, that adds up to about 2 or 3 months. And it leads to an interesting effect, because now, even after your insolation is gone, you're having condensation of large volumes of water in the poles. That releases energy. And so the water vapor is working basically like a battery. When you have energy surplus at the poles, it evaporates water instead of just heat on the surface. And when you don't have radiation, it condenses water and gives you a heat source. And that's enough to actually keep your poles warm for several months into the winter. And so your poles can actually become just about as warm as your mid-latitudes. Your temperature gradients shift. Now, I know for astronomy, that's a pretty, we're talking about really small numbers, but from a dynamics point of view, changing your temperature gradients has implications for your circulation. While a solstice condition on Earth, you'll expect to have your Hadley cell and your Ferrel cell, something like that. For our high obliquity case, with water, we don't get a Ferrel cell at all. This is a little weird. Why don't you have circulation right where you have most of your energy imbalance taking place? This also means you don't have baroclinic eddies, you don't have storm tracks. Pretty weird dynamically. And instead of trying to prove this to you that it's the water vapor mathematically, we do that in the paper. If you're into that kind of thing, you can check it out. But I'll just prove it to you by taking the water out of the model and running it dry, and you get your Ferrel cell back. And you can, even if, I know Ferrel cells is kind of, niche, but I like to sort of show this, hopefully by comparing the high obliquity case and the low obliquity case, you can appreciate the similarity there of just the power of water in this model of taking you from a really high obliquity planet, making it kind of look like the low obliquity case. And it was a really fun result for me in the sense of forcing you to think about water not just as something we're looking for, but being really critical as an initial assumption in your studies. Because it doesn't just matter how much water we put in, but also where we put it in. Other groups have looked at what happens when you put the water in the low latitudes versus the high latitudes. It'll make a really big difference. How much water we put in is going to change these results substantially. And this is just for an Earth-like case around a G dwarf star. Water will matter a whole lot more for every other planet we're going to be talking about today. It's just sort of the initial simple case where it's a pretty mild impact. All right, so now on to exoplanets. I'm going to be talking about M and K dwarf stars, like I said. It's a little hard to juggle both, so I'm going to start with the M's, and we'll hopefully make it to some of our early results about K's at the end. I'm sure everyone here is pretty familiar, so I'll skip this background a little bit. M's are really common. They're long-lived. It gives you more time for life to develop there. That's where we have most of our Earth-sized targets right now. TRAPPIST, yay. This is where we're going to be looking for Earth right now. This is where we can, write a grant to say we're going to study an Earth-like planet. And M dwarfs, yes. This audience already knows all of this. Great. So we're going to be looking for an Earth-like planet around an M dwarf. What does that mean? What is an Earth-like planet around an M dwarf? What is our best-case scenario, our dream Earth-like case? If we're hoping for our Earth twin, what does that mean around an M dwarf? Even best-case scenario, we have to adapt to the fact that we're orbiting now around a red star. So here I've plotted, the sun, a K, and then both the TRAPPIST and AD LEO. I'll be showing you results for AD LEO today. Longer wavelengths, I'm sure you've seen this plot many times before, but since we now have a lot of our radiation coming in the near infrared, that's going to impact every wavelength-dependent climate feedback. Pretty much every climate feedback that you have heard of and care about. One. I think it's 3.5. Here is ice albedo, for example, one of the bigger changes that you'll see. So while we typically think of ice as being super reflective at shorter wavelengths, right, for Earth's peak radiation, a lot of that's bouncing back. If we look at our longer wavelengths, pretty much nothing. So forming ice over an ocean on an M dwarf is not going to be a strong change in your albedo. Everything that we think about for like Milankovitch cycle, snowball Earth, is going to play a much smaller role here. In turn, water vapor also becomes more dicey for our M dwarf planets. So while on Earth, we typically think about insolation in the sense that it comes in right at the peak here. There's not too much absorption of incoming radiation. It just heats up the surface, and then the surface re-emits, and then that thermal emission is going to interact with the greenhouse gases. Here, for our M dwarfs, you'll notice that there's already a lot of absorption at the peak. So you're going to have your atmosphere absorbing both incoming and outgoing radiation, and that sort of foundational greenhouse effect is now not behaving quite the same way. We'll be coming back to this, so there will be more details. Other things to keep in mind, these are dimmer, they're smaller, the habitable zone is way closer to the star, and so we expect rotation for a lot of these planets. So yeah, you get a little animation there in case you've, never thought about this. Permanent day side, permanent night side. We expect that means, hotter day side, hotter night side. We're already pretty far from Earth-like, right? But still, this is as close as we can really hope for. So what does that mean for us? I want to give a little framework since we're going to be talking about the dynamics of a tidally locked planet for how we're going to think about it. Again, it's not very Earth-like. So in terms of radiation, all of your energy is coming in on that day side. Both the day side and the night side are emitting thermal radiation because they are not at 0 Kelvin, we hope. And the night side is, for now, only has an arrow leaving it. For this to actually reach steady state, you need one more arrow. You need advection. For the talk today, advection is entirely in the atmosphere. We are neglecting ocean energy transport for a variety of reasons. To name a few, it is computationally efficient to do so. 2, we do not expect the ocean circulation to do very much energy transport on an M-dwarf planet. A couple other groups have done studies to show this. Winds are weaker, you don't have good buoyancy forcings, you don't have that ice albedo feedback to help drive a deep mix layer and an overturning. And so we have pretty low expectations for the ocean energy transport, even with a deep ocean. And as we'll talk about today, we don't really have great hopes for large global oceans on an M-dwarf. That's a huge water reservoir, and this entire talk will be about how hard that water reservoir is to keep. And so if we then sort of have more modest expectations for the ocean, and it's broken up into smaller basins, it's already not going to transport that much. So we feel pretty comfortable in saying that the atmosphere is going to be doing the heavy lifting here. If I say advection or transport, I'm talking about the atmosphere for this talk. All right, that's the background. Let's actually get to some results. This is our most Earth-like case that I'm just going to use to introduce simulation. We're running ExoCam, the GCM. It's based off of the CSM model, so nice, clunky, all the bells and whistles GCM. We put this so that it's receiving the same amount of energy from 80 Leo as Earth receives from the sun, so that's a 34-day orbit at 0.154 AU. Earth-like in terms of everything else, mass, atmosphere, we do pre-industrial. Slab ocean, so no ocean energy transport, but there is water at the surface. And to keep it simple, it's just water everywhere. And yeah, as I said, 80 Leo. Here's our temperatures. Surface temperature on the plot, we'll be seeing a lot of these, so just to get situated, substellar point is right at the center. We're looking at the day side in the middle, night side on the edges. The night side is below freezing. Day side, nice and balmy, temperature similar to what we have outside today. And habitable zone, habitable region, in sort of hand-wavy terms, anything between 0 and 50 Celsius is marked with the hash marks throughout the talk. Yeah?
Tidally locked planet, or?
Yes, tidally locked, synchronously rotating. 3. Yeah, it's a full 3D clouds. Yeah. Yeah, CSM is basically as many of the bells and whistles as you can throw at it. And yes, so synchronously rotating, so hence you have this big day-to-night contrast on this planet, and the terminator is marked with the little white lines there at the 90 and. All right, so it's still sort of just our most close to Earth-like that we can put together with 80 Leo. To point out what the water vapor is doing, since I've been talking about set it up of water vapors being messy here, let's see what it actually does. So every aquaplanet you throw around an M-dwarf star is going to be cloudy. That's just across the models. It's just incredibly cloudy. You can just look at it up here. Cloud fractions of basically 100% at the substellar point and doesn't drop very much until you get close to the terminator. That means that you're going to reflect a lot of your radiation right off the bat off of the clouds, but whatever does make it through, wherever there's water vapor in the atmosphere, and here you're seeing a cross-section, it's going to start absorbing radiation as that radiation works its way in. So you get a lot of absorption right at the top. You encounter another little pocket of water vapor, you get absorption again. And so if we look at what's left of the stellar radiation, there's very little that actually makes its way to the surface. So the substellar point is actually quite dark, largely due to this amount of water vapor in the atmosphere. So I like to joke, since I've also given the talk to recently at AbSciCon, you're going to be thinking about this planet instead of thinking about Synex, a bit dimmer, darker, redder, darker than that really, but you can only do so much with vectors. Okay, cool. You have your picture of an M-dwarf aquaplanet. This is our Earth-like case, fractional habitability with our definition about 32%, so pretty nice. And we jokingly call these our eyeball planets. Early days, that term sort of popped up. In the artistic representation, I think you can tell why. And you get that little island of habitability on the day side. All right, let's spread out. Let's look at the rest of the habitable zone and what other climates we can hope to see. So as long as we stick with an aquaplanet, we go from pretty much colder planets with a little island. It just sort of shrinks as we move out. We eventually get to a planet where we melt our night side, and you start to sort of have moderate temperatures on the night side. And then we hit a runaway greenhouse effect, and that last one's there just for sort of a sense of scale here. I will get to water and habitability and the climates in a minute, but as I said, I'm a climate scientist. Atmospheric dynamics is my go-to, and I'm going to drag you a little bit into the weeds for like 2 minutes here to show you some quirky things that happen on these planets as we move from the outer to the inner habitable zone. So if we look at the radiation budget, you'll see the insolation coming in is increasing as we move in. We take out the radiation that's reflected by the clouds, the top of atmosphere albedo, because it doesn't really matter for the climate, and they get the dashed line there. That's the energy that's actually going to be interacting with the climate. And then our emissions, which we're going to be calling long wave. I know that's not, long wave by every definition, but that's our term here today. And that's just what the planet's emitting up the top. You'll notice if you compare as we move inward, the day-side emissions don't increase very much. They're pretty stagnant. These atmospheres are so optically thick, there's not that much they can do to emit more energy than they already are. And so most of the adaptation is night side, your night side increasing to balance out the increase in day-side incoming stellar radiation. And so that means is that as you move inward, you're going to increase your imbalance. So you're further and further from radiative equilibrium, and more energy needs to be transported from the day side to the night side. So this is, okay. But if you look at that naively at the warmest planet, you'd think that must need a much more intense atmospheric circulation. More imbalance, the atmosphere is going to be doing the work. That's actually not the case at all. That has the weakest overturning. So weaker winds, there's less mass actually making its way from the day side to the night side of the planet. So if we think about this in terms of tracer transport, maybe short-lived biosignatures and how quickly they're going to mix in this atmosphere, the colder planet will actually be better mixed. There's literally more material being shifted around in the atmosphere. And the hotter planet will actually have much slower overturning. So mixing timescales would be longer, tracers would be less mixed, winds would be weaker, and et cetera. But is that viable? I just told you have a larger energy imbalance and you have a really weak atmosphere. And this is where the fun little bit of dynamics comes in. This works pretty much just like Earth's Hadley cell. The upper branch of this circulation is transporting a lot of potential energy. The lower branch is transporting a lot of sensible heat, energy, it's actually just formed there. They're competing. Same thing happens in the Hadley cell. And on Earth, we know that this just means that the net result is just the balance of the upper and lower branch. That's very little to do with the overall intensity, but rather this competition between the two. And to show you this a little bit numerically, last slide in the weeds, I promise. I'm plotting here the energy flux divergence, and you're looking at a vertical profile of the area near the substellar point. So don't worry about the energy flux divergence. I know it's jargon, but if it's positive, that just means that area is exporting energy. If it's negative, it means the area is importing energy. You can see that the upper branch of that circulation is exporting energy, lower branch importing. True for the colder, the hotter case. And all you really need to sort of see in this squiggly line is that the upper curve is very similar to that lower curve. Most of this cancels out. So hence the intensity of the overturning doesn't matter that much. It's all in the details and the nuances of the structure and how these two compete with each other. So if you then vertically integrate and integrate across the entirety of the day side, we get our net transports, which is what you're seeing below. And I just want you to focus on the white bar, which is the total. That's quantifying exactly how much energy is going from the day side to the night side. You go over the entirety, integrating the entirety of the day side, so that's the total transport. And you'll notice that it increases as we move inward. So that's actually a more efficient cell. So all of this to say that Your planet that is efficient at transporting energy is not necessarily efficient at transporting anything else, like tracers or that you'd be using for biosignatures. So you can have these sort of conflicting realities there. And the reason we do all of this deep dive into understanding how efficient the cell is and how these can coexist is because we were looking to see if we could find a different climate regime. Because when you run these aquaplanet simulations, your planet just consistently goes from larger temperature gradients up far on the colder end to a pretty homogeneous planet by the time we're at the inner habitable zone. We can see this by maximum and minimum temperatures in the plot at the bottom. You can also just look at the contour plots above to see that you get a pretty smooth transition. And the artistic version of that is a snowball, eyeball, maybe a global ocean if we're lucky, and then runaway greenhouse. Now, of course, this is not the picture. This is not the end of the story. I will now tell you why this is completely messed up and doesn't work at all. But for a while now, these were the climate regimes we could find. We were very bothered because we hadn't found a few climate regimes we originally expected, in particular the Terminator habitability climate regime. And so we started digging into this. So I already told you the first one's a runaway, so we're not really counting on that one too much. What's wrong with the second warmest planet? Well, that one's not actually technically in the habitable zone. It's past the moist greenhouse limit, so that one was just a little deceptive there. It's pushed a ton of water vapor into the upper atmosphere, and that means that water would suffer photolysis and escape. And so we don't expect this planet to look like this for very long, so it'll slowly morph into a much drier planet. And we're left with our mid and outer habitable zone. These two have a very different problem. As soon as the night side freezes over, you start being endangered by night side cold trapping. And that switch happens very quickly in the M-dwarf habitable zone. You go from melted night side that passes the moist greenhouse limit to a frozen night side and night side cold trapping. And just in case this term is new to you, I'll do a really quick what is night side cold trapping interlude here. On a synchronous planet, all of your evaporation is taking place on the day side. That's where your temperatures are amenable to evaporation. You have liquid surface water, and you have enough heat to actually move that water vapor. It can either precipitate on the day side. Precipitation rates are actually pretty low. It doesn't rain that much on this planet. Or it can condense as snow on the night side. It can technically snow on the edge of the day side, but really the interesting snow is happening on the night side here. There's not a great mechanism for bringing it back to the day side. In terms of a water cycle, your atmosphere is very efficiently taking water to the night side. Return flow is literally glacially slow. Literally. No, I have to find some puns where I can. And so you will have a backlog of water on that night side. You may ask, how fast could this possibly be if just the atmosphere doing that work? You may ask, how long would it take to move all of the water in Earth's oceans from the day side to the night side? You're looking at 100 to 300,000 years on the planet. So that is nothing to a planet. Even if, we're off, like with the flow, this doubles, this triples, it pretty much doesn't matter. We would not expect to find a large-scale global ocean on the day side. So, all right, our aquaplanets do not look great if we really dig into that water budget. As much as, when you run the simulation, they look like they're at steady state. In the nuances, they are not. And we would not expect to find to look like any of these. If we then account for additional issues with M-dwarfs that we already have known for a while now, that one, they might have less water delivered to them from the very beginning. So maybe we don't really have a reason to expect that they're going to have a bigger water reservoir than Earth in that sense. They may also lose a substantial, if not entirety, of their water reservoir during the pre-main sequence phase of the star, because if it's currently in the habitable zone, it didn't used to be, is my simple way of explaining that. And so there's not a great argument for an initial large water reservoir. We do have now considerations of mantle outgassing and potential water sources later after the star has finished its main sequence phase and entered into the main sequence phase. So we might be able to recover some of it. That's kind of a point of debate. But we don't have much motivation to think about these planets as starting with that much more water than Earth would have had access to, and probably less. And then if we also account for everything I've been talking about now in terms of loss, we should at least be prepared for an a drier day side. Because in the best case scenario, on the night side cold trapping, you'll still retain water on the planet, but we're not talking about a global day side ocean in any scenarios. So to that end, I'm going to take you to the other extreme now of a pretty arid planet. That is not to say that there aren't intermediate regimes for us to find. There's a lot to still explore here. We've, as a community, have stuck around aquaplanets for probably a little too long, and there's much more nuance to be explored on a land planet. There's a lot more parameter space when you switch over to land, but I'm going to just show you the extreme so you can see how much it changes once we do a water-limited planet. So not completely dry, but limited. For example, these two simulations were run with a sandy surface, no surface water, but it's initialized with atmospheric water vapor. We did varying amounts of water vapor, it doesn't matter too much. So it's pretty arid. We joke it's our Tatooine planet, if that helps. And you'll notice that these have much larger temperature gradients than the corresponding aquaplanets. In fact, the dayside temperatures exceed habitable limits. And so you will notice your habitable zone is no longer a little island centered on the substellar point. It is now a ring-like shape. It's being pushed towards the terminator, hence now quirky little nickname for them, our terminator habitability planets, which were predicted in science fiction, and we didn't find for many years because we kept running aquaplanets. You will not be able to get it. And if you want to be a strict proof of why you will not find it with an aquaplanet, you can check out the paper, but you will not find it running an aquaplanet. So what changes here? What happens when you run a land planet? The radiation coming in is a little bit more like our intuition for Earth. You'll get less reflected by the clouds because you have fewer clouds. More of that radiation is going to just stream in through because there's not as much water vapor having like the massive absorption feature in the atmosphere. You're actually heating up the surface of the planet, and you're actually shining some light on the surface of the planet. So in that sense, it's a bit more intuitive. The circulation looks a lot like a cold planet, even though it's pretty warm on this Earth-like case. So you'll see a more well-mixed atmosphere, so in terms of tracers, well-mixed. But in terms of the energy budget, there's not as much transport happening because it doesn't need to happen. These planets have a more optically thin atmosphere. They're very competent at emitting, cooling themselves off on the day side. So you'll see that the thermal emission profile peaks on the day side substantially. In terms of radiative imbalances, they're much closer to balanced, the aquaplanet. And so they don't need to transport that much. You're still getting a lot of that cancellation in the cell. The individual terms are much stronger. They're moving more air. The top and lower branch are doing a lot more activity. They have the individual terms are all bigger. When you integrate it out, spectacularly inefficient, which is why you can sustain large temperature gradients on these planets. It's also a nice reminder because when you look at the energy budget, the water vapor doesn't do very much. The latent energy term not even visible on the plot. But instead, water changes the vertical structure and controls all of this. So this is due to water, even though the water doesn't impact the energy. So water controls this in correct ways. All right, so this is why we can sustain large temperature gradients, why we can find terminator habitability on a land planet. I'm coming to you guys right after AbSciCon right now, and there, we're going to talk about habitability. So I'm going to go through a couple of slides just talking about what these planets might offer in that sense. I mentioned you're getting more radiation at the surface of the planet. You can see here the radiation versus that hash mark habitability region. It's kind of hard to see even there, so here's a line plot. Just to really hone in on that point of the radiation reaching the surface of these planets, which is what I'm plotting here, is much more Earth-like in terms of watts per meter squared on the land planet than on the aquaplanet. Anywhere on the land planet day side, you're going to get more radiation than on the aquaplanet surface. And so even though your habitable region is being shifted towards the terminator, it's still better lit than it would be on an aquaplanet. So, in terms of thinking about intensity of which life could possibly even develop on these planets, or what kind of volume of biosignatures you might hope to ever expect to find, these could be potentially different scenarios to consider in terms of photosynthesizing life. Sometimes when I'm talking about stronger and weaker overturning, people ask, does that mean really strong winds? Is life going to be torn apart by hurricanes? While the high altitude winds are significantly different, and actually the land planet gets closer to values we see on Earth in terms of the jet streams and so on, and those are technically hurricane speed winds, that's only just technically at the surface. It's all pretty weak. Aquaplanet, land planet, it's all very mild. At the Terminator, you just get a nice breeze. So no worries there. Okay. So then, I'm sure there's a lot of observers here who could do this slide better than me, but less clouds is pretty nice for transmission spectroscopy. Many teams have shown this result. I'll borrow a figure from TAD here, but I'm sure you've seen the many papers recently highlighting this point that less clouds will allow us to get a clearer picture of the composition. And the point I want to highlight with these results right now is that even if these land planets do have some clouds, they will be centered on the substellar point, or shifted a little bit in that general region. And that gives us sort of the opposite picture that we get with the aquaplanet. Because the aquaplanet, your region of interest for habitability, is exactly the region that is most covered by clouds. As for the land planet, since your habitable region is being shifted towards the terminator, you will get less cloud coverage over your region of greatest interest. So maybe someday we'll find a way to leverage that to get a slightly clearer picture on these planets than we would hope to get with an aquaplanet. There may be some extra hope there. In terms of emissions, I just want to highlight that these look a bit different. I'm going to just focus on our two most Earth-like cases here, just to point out that they do have a very different profile. An aquaplanet will actually have a minimum emission on its day side because of that cloud coverage, whereas the land planet will actually maximize when you're looking at the day side. So in a lot of ways, it's more intuitive. And your difference between your day side and your night side emissions are significantly greater. And since your day side can become hotter than habitable limits, you can actually have much greater values of day side emissions on a land planet. These are just two sort of borderline random cases of our closest to Earth-like. As we explore a broader range of land planets, we might find some advantages to leverage there. All right, so I've been talking about habitability in terms of temperature. I should at least pause and acknowledge that it's also a function of your water availability, and I've been showing you a very arid planet so far. But there's one little quirk of these land planets that could be making them a little extra exciting, and that is if they had a water reservoir at some point, and a portion of that got locked on the night side in the forms of glacier, we can work with that. So you form a night side glacier. Glaciers flow. We know that from our experience on Earth. And even though that flow is very slow, you will tend to have some liquid water accumulating at the end of that glacier near the terminator. For the purpose of actually adding some numbers here, this is very hard to pinpoint right now. These models don't include glacier dynamics, so we can't fully find a balance, but we can take some numbers off of Antarctica, take the flow rates we get at the edge of the glaciers in Antarctica, and sort of say, like, well, what would this look like for a very small, like even a 10-meter glacier, to get a very low limit of, like, what's the minimum flow we might expect for an Earth-like planet. We can get, a 10 to minus 2 kilograms per second flow. This is very much just trying to get a ballpark sense for what's happening here. Hopefully one day we'll have glacier dynamics and be able to actually do this in a more nuanced way. But the reason I'm highlighting this is because even though this is a weak flow, we can leverage the fact that evaporation is pretty weak at the terminator. As I said, you evaporate more on the day side where your temperatures are higher. As you get towards the terminator, you're very close to freezing, but not quite. You're going to get lower evaporation rates. And so if you have a surplus of water that makes it to the day side, it will for sure evaporate. You're not going to accumulate it there. Right at the terminator, we can actually potentially have surface water accumulation, because if we look at evaporation rates in the aquaplanet, and we treat that as an upper limit to evaporation, and this is reasonable to us because an aquaplanet will evaporate if it can. It loves to evaporate. There's no evaporative resistance. There is infinite water source there, so truly nothing stopping it from evaporating. And so we can take the rates near the terminator and say that that's our upper limit for evaporation. And you'll notice that it is many orders of magnitude smaller than the ice flow rate. So this will all depend on topography. It will depend on the nuances of the geothermal heat rate of the planet. It will depend on how much of a glacier you formed or didn't form. But it opens the door for some degree of surface water accumulation right around the terminator. So here's our little picture of that. If most plausible would be to say maybe lakes and rivers, sort of smaller bodies of water. If you're an optimist and topography is in your favor, it could be a small ocean. If you're a pessimist, then it's soil moisture. But all of these hold some prospect for life, and you now have surface water accumulating very in the region where you have temperate climates. So even though we're working with pretty limited water reservoirs on these planets, that doesn't mean we have to be pessimistic about potential habitats on these planets. All right, so general picture. M-dwarf habitable zone is very hostile to large water reservoirs, to our aquaplanet-like scenarios. And so we're hopeful about what we can do with more limited reservoirs that might be achievable with later phases of outgassing on the planet. So this is our optimistic scenario. How does this picture change for K-dwarfs? And that's what we're sort of shifting to now, to sort of think about what changes. I only have a few preliminary results here today, but for fun, I want to just show you the contrast of these simulations and how they change when we run them with a K-dwarf. And so I'm only going to show aquaplanets that are in synchronous rotation. There's a whole lot more to be said and different regimes to consider here as well. But here is our habitable zone for a K-dwarf. You'll notice that we're going into higher values for a solar constant here because it takes a lot more radiation to push a K-dwarf into a runaway. You'll see similar trends to what I talked to you about before. The colder planet here has a stronger overturning circulation. The hotter planet has a weaker one for the very same reasons as before, the efficiency of the cell. So in terms of tracer mixing versus energy transport, again, you get that same dichotomy. In terms of the edge of the habitable zone here, your moist greenhouse limit is being reached only by our 2700 watts per meter squared planet. So that one is our water vapor escape planet at the edge. And you'll notice for the remainder, you have a frozen night side. And so coming back to our night side cold trapping, here's where I find the K-dwarfs entertaining. They have much weaker night side snowfall. So they get more rain on the day side, substantially more than your M-dwarf, and they get less snowfall on the night side. Instead, they get this little ring of snowfall on the day side. It's kind of fun. It doesn't really matter that much because it's snow that's falling on open water, so you don't have to worry about it. It happens due to low-level turbulence at the edge of the sea ice in the ocean. And remember, ice albedo is going to be a little bit stronger for a K than for an M, so you get a little bit of this turbulence feature. But we're not worried about it because it's just snow falling on water. It's fine. On the night side, you have much less snowfall if you compare them one-to-one with the M-dwarfs, and that snowfall rate drops substantially as we move into the outer habitable zone. If we use the same timescale we did before of how long it would take to trap all of the water in Earth's oceans, you'll see that you go up a couple orders of magnitude as you move out towards the outer habitable zone. Now, as I said, the return flow, that ice flow, that basal melt of the glacier, all of these we can't pinpoint right now. It's too planet dependent, topography dependent. But if we assume that it's somewhat Earth-like, or something that had basal melt or geothermal heating rates comparable to what we see on Earth, this coldest planet here would not be subject to night-side cold trapping. Basal melt would take care of this one, and it would be able to maintain dayside water. Our Earth-like case is pretty borderline, really close in terms of the rate that you could expect water to return versus be transported. So that one depends on how optimistic or pessimistic you are, and then as you move in, you still get nice cold trapping. And so while we can't pinpoint it without a better understanding of the return flow in the night-side glaciers, we can be optimistic in the idea that there is an outer limit to night-side cold trapping in the K-dwarf habitable zone. And so while the M-dwarf hazards are pretty much spread throughout the entirety of the habitable zone, for the K-dwarfs, those hazards are concentrated at the inner. And so we actually might have hope of finding a synchronous planet with a dayside ocean in the K-dwarf habitable zone. Whereas for the M, that would be quite an ask to hope to find. And so that's the direction we're going in now, of trying to put more constraints on the climate regimes we can expect and how the K-dwarf systems would vary compared to the M-dwarfs. So just to sort of leave a few summary slides, if for any ocean modelers, if you're really keen on a dayside ocean, I urge you to think about K-dwarfs. We've ignored them for too long. For M-dwarfs, I think we should be open to the idea that they're just going to be drier, but that doesn't have to be bad news. It can be good news. Land planets are exciting. They're fun. They can have a much broader range of climates, and there's much more diversity in terms of surface types and what we might expect to see happening on them. So there's a lot to explore that we haven't at all. We've given much less energy to them in terms of researching their climates. They can be in Terminator habitability configuration, which is fun, but also promising in terms of offering habitats for life to develop, and potentially making life a little bit easier to see, as we look to the future. This might be an easier place for us to find life. And and with that, I will stop questions, and in case you want to follow up on any of these, I will leave a QR code that I'm quite proud of there. Thank you.
Awesome. Awesome talk, Anna. Oops, sorry, didn't mean to scare you. So yeah, we have time for questions. So if you're online, feel free to raise your hand or post them in chat. Or if you're in the room, just feel free to raise your hand. Bobby?
Great work, and really fascinating, inspiring. One question about greenhouse warming. I assume you had a sort of static amount of CO2 in the atmosphere, but of course Earth's CO2 and other greenhouse warming burden has changed dramatically over time, and I know that's not something that's easy in any of these GCMs, but what do you think, how do we start to incorporate that more realistically? Because as you change from land to water to tectonics to other things, this is all going to change. So what are your thoughts on that?
Yeah, it's a challenge with doing the GCM work because you're not going to have your weathering cycles properly accounted for in the GCM. And so one of the sort of next steps we want to do is a bit of a sensitivity study there to the atmospheric composition to see how much this changes as we tweak it. And so we are sort of planning to try to at least look into how these results change. It's just there's always more parameter space than we can cover. And so I like to err on the side of like the optimist of Earth's system equilibrated near here. So like I start there and work my way out because we don't really, there's not a better argument for any specific composition, but it definitely is a parameter space we have to cover.
Yeah, this was really great. I think I have a question similar to Avi's, and I think the answer is probably that it's too hard to include in the model. But I've heard that land planets can be complicated for habitability based on what we know about plate tectonics, which is incomplete and complicated. But what I've heard is that land planets might have a harder time having plate tectonics because I guess you need water to lubricate the plates to go into the mantle. And so that could complicate the carbonate silicate cycle on land planets to regulate their temperatures over long time scales. So my question, which I think is an impossible question to answer, but my question is, are there prospects for incorporating these kinds of feedbacks into these kinds of models?
Okay, so let me take that sort of as two parts. I have seen sort of some studies getting at the sort of tectonics for the land planets. They usually do look at sort of the arid completely. I think they've looked at the completely dry case. And so my sort of sidestep answer to that is don't necessarily have to expect completely dry, especially as we think about, maybe outgassing would allow us to retain some medium-sized water reservoir. That could be actually kind of an Earth-like scenario, right? If we get into that like 30% water, we don't have to worry about this too much. So that's my sidestep to your question. But yeah, I don't know that anyone's gotten to that point. I've been sort of asking about glacier dynamics for a while. That's like, maybe, but not, that's already a bit of an ask. Yeah. So I imagine that would be like even further down the pipeline.
Yeah, I feel like people parameterize plate tectonics in like box models.
Yeah. So box models are an option, and there might be some creative way of sort of running
that to GCM.
Yeah.
Yeah.
It would not be impossible, but it would require a bit of a long-term commitment to
for sure.
building that.
For sure. Thanks.
But, hopefully if people are convinced that land planets are worth attention, we can start to explore that a bit more carefully.
Something beyond land planets. They're only half land.
Yeah.
I mean, they're all,
I've been sort of using water limited as a contrast to aquaplanets that are, infinite water, but I'm open to terminology work there.
Yeah, and I would agree with what I've seen, that as long as you have some water, that really helps the tectonics going. That's a great question. I don't think we do. We should look at that, yeah.
First, did you have a question?
You had one early on, yeah?
Yeah, this is a bit of a more general question, but since I'm an outsider here, with respect to the field, I'm aware that there are just many significant challenges with life and habitability for M dwarfs. So I'm a bit befuddled by the obsession with M dwarfs in this community.
Okay.
Right? So I just want to, it's not related directly to your work, but what is your general take on this and the status of this?
The community has flip-flopped on a lot of these issues for a very long time. And so I take sort of the moderate approach of we should explore them because they are abundant and we have access to them now, and in our lifetime they're like a pretty good bet as to where if it does exist, we might be able to find it in that 50-year time scale. And so I think it's worth exploring for that reason alone. Plus, many of these challenges we've shifted our perspective over time, right? Like 3 years ago when we started this work, and I had sent a student to a conference and they were told, like, how dare you think there's water in an M dwarf? There's absolutely no water there. And now we think about mental outgassing and other water sources, and we have a more optimistic view. And so there's a lot still to explore before we cast them off or commit.
I think my questions should be easier. The first one is you talked about the water vapor loss. You didn't say the mechanism you were using. Is it photoionization or just like the expected winds, or what is the dominant thing you're thinking is removing the water in your simulations?
So here we're using I drew the line based off just the casting limit, which is based off of, I think, just photodissociation rates, which would be a little bit lower for an M dwarf.
Yeah.
So that time scale order of magnitude would be a little bit, I think order of magnitude is okay, but there's like a factor there of decrease. But it's very far past the casting limit. And so it might be a little bit, if we drew that line, the line would have to move a little bit, but.
And the other thing I was thinking about was in your ring water sea scenario, that's the same scenario where you have this like, I don't know, the breeze is pointing from every direction at the surface level, at least towards the substellar point. So does that get factored in with your cloud model? Because you have air flowing across the liquid water and then going into the like warming air coming straight in. So
yeah.
I mean,
I don't quite get the question. If it would impact the cloud?
You have water around at the surface, like liquid, and then you have the air is all coming in across it, and then going to the middle of the arid side.
So you're asking if you had that sea, if it would change your cloud coverage?
Yeah, or at least get some interesting precipitation, or whether that's included.
Yeah, so it's not included yet. It's actually sort of a next step to run a simulation where we input that water. It's a little tricky because, as I said, your water source is glacier water, which is not in the model, and we can't really force it to be there. And so if you do that simulation, it'll never actually technically be at steady state. So, it pushes you into, you can do it, we can look at it, and we will, but we sort of have to be a little bit careful about how we do that analysis. I would expect, given the overturning structure, that you'll get some low-level activity. But it will be shifted inward because it takes a while for the wind comes in very dry and very cold from the night side. And so even though it's picking up water vapor as it passes, there's only so much it can evaporate there because it's still pretty cold. And so I wouldn't expect too much cloud formation there until the geometry starts converging the flow closer to the substellar point, and that's sort of like mid-range. And that's where you get a lot of turbulence, the boundary layer pops up. And so I would still hope that the clouds would be more towards the substellar point than that region of the water band. But it's worth testing to make sure, because right now that's off of the intuition of flow. Okay.
Thanks for a nice talk. My question about the AD Leonidas, that you selected AD Leo, right? The first. This is one of the most craziest stars I know, because we observe now, we detected signatures, coronal mass ejections, super flares, 10 to the 34. So the X-ray and UV flux, 1,000 times during solar flares, greater than the Earth receives from the sun today. So this is one of the most volatile scales. Why did you select this case?
It was purely a convenience thing. We wanted a brighter star than TRAPPIST. Because TRAPPIST is sort of this quirky little, really packed-in case. It's one of the little cases where you actually have a bit of a rotation effect. You can still get nighttime cold trapping on those planets, but it just looks messier. So we wanted a slightly cleaner case with a brighter star. And AD Leo was just convenient. We had the spectra ready to go for the model, binned appropriately to run it with the model. But these results would hold for anything in that general bright M-dwarf range. It's not really specific to AD Leo. That was just a convenient take.
That would probably put some constraints on the atmospheric pressure. So did you use the one bar?
We kept it as Earth-like. Anything that we can keep Earth-like, we kept Earth-like. Other than the synchronous rotation, the stellar spectra, and so on.
Thanks.
Hello, good talk. I'm still new to kind of the exoplanet community, but I'm learning more about different things that's been going on. And one thing that we're seeing in models for Mars with the Hadley cells is that because of the higher eccentricity of the planet, the Hadley cell reacts differently at different parts of your orbit. Now, how would you expect this kind of stuff to change if the eccentricity was higher, and maybe the Hadley cell would react like a cross-equatorial Hadley cell like it is on Mars?
Eccentricity would be actually quite interesting for these planets. Off the cuff, it would be hard to sort of guess the Hadley cell or the returning circulation on this case, but it would be kind of fun for them because you would get a little bit of extra melting periodically. That's also something we've discussed in terms of if they had a small wobble or something like that, because anything that would give you a shift in your melting line of a couple of kilometers, even if it's on a couple of weeks that the planet melts a little bit extra, a little bit less, it would give you an inflow of surface water, which could be potentially really exciting for surface water accumulation in life forms. There's a lot of discussion now of life that forms with periodic water availability. And so if any of these things happen, it would actually make it even more exciting for us, whether it's a wobble, eccentricity, but there could be some details there in terms of the circulation that are worth exploring. We just, again, another part of that parameter space still have to be looked at.
Thank you.
Anna, I had one, and also just great talk in general. When you were showing the figure with the surface wind speeds, and you had the tropical force, maybe Cat 1 hurricane speeds. So I guess the difference here, if I'm understanding correctly, or my question, I guess, is that is a constant wind, though, right? It's not an isolated event.
No, just put it there for reference and a sense of scale.
Right.
This is more, think of it more like the jets on Earth. They're just there.
Right. So I guess I'm just curious if anyone has looked into when you have this sort of constant wind, especially if you do have some land, are you getting just long-term frictional heating of the wind on the surface of the planet?
Well, the surface winds are pretty weak.
Oh, I'm sorry. I thought that was the surface.
No, those were the high altitude
Oh, I
winds.
misunderstood it. Okay.
So those are the high altitude winds. Once you get to the surface, start clicking back out.
No, I misunderstood.
The surface winds are very mild, so we actually don't worry about it in that sense.
Gotcha.
And there's an interesting point there of if you just have constant wind, even if it's weak, maybe you'll get, something interesting there. So I wouldn't say it's not worthy of exploring, but We're not worried in the sense of like blasting life with a strong,
Right.
hurricane force wind, because that's high up, and as we know on Earth, we survive with this every day.
Right. Gotcha. Thank you so much. I think we have time for maybe one last question. I'm just looking, see, okay.
Considering that the originator of ExoChem was Eric Wolf,
Yes.
and you are Anna Lobo,
Yeah.
I was wondering if your name has to be associated with the wolf species to use ExoChem.
Yeah, I told Eric I was stealing his branding and decided to just outdo it in the talk, so it's a bit of a mutual joke at this point. So, yeah.
Awesome. Let me just double check online to make sure there's no questions there. Right. Not seeing any, but I think we're right around time, so let's thank Anna again for the awesome talk. And I think Anna might have some time this afternoon, maybe, potentially, if anyone wants to have any more discussions, so just get in touch. But thank you, everyone, for joining us today, and thanks for those who are joining online, and we will see you on Monday at 11 for our next exoplanet seminar. Thanks, everyone.